Hello, everybody. Here we are going to be looking at our molecular geometry through molecular models or molecular modeling. This is one of the few labs that I basically will not let students miss. And so, in the event that someone is sick or has something planned and can't come, you're going to be doing this lab virtually, which will work just fine, but it's really going to help you understand what's going on. And if you're in Chem 120, this is for chapter 8. And if you are in Chem 131, this is for chapter 7. All right. Welcome. Okay, so here we are. What we're going to be doing for working through this is I'm going to be working through a series of things. The first thing I'm going to do for each one is count my valence electrons. And the second thing I'm going to do for each one is draw a Lewis structure. And we would be doing this in class as well. So draw our Lewis structure. And then the third thing we're going to be is going to be determining um, our number of bonding pairs. And number 4 is going to be our number of lone pairs. And number 5 is going to be our total number of electron pairs. Hang on, I just realized something here. This should say bonding pairs. Total number of electron pairs. And then I'm going to be doing number 6, and I'm going to do this for 12 different compounds. Number 6 is going to be, we're going to be determining the geometry of the electron arrangement. And number 7, we're going to be determining the geometry of or shape of the molecule itself. Okay, so let's begin. Okay, so first of all, we'll take a look. A lot of these you've already seen in class, so this lab is intended to be basically a complete review of the chapter that you're working on. So to count our valence electrons on this first one, we have 4 from carbon, and we have 2 oxygens, and we have 6 from each oxygen, and that gives us 16 valence electrons, and that's number 1. And then number 2 in here is it says to draw a Lewis structure. So we're going to start by basically, that was a little bit too close to the edge. Go. So we're going to put in our oxygens, just like so. Now that's got 2, 4 electrons so far. So we're going to start putting in our electrons here. And so we've got, oh, I'm not quite, okay. And okay. So 2, 4, 6, 8, 10, 12, 14, and 16. Okay. But the problem with this is that we have not enough electrons on carbon. So we're going to go ahead and take that back out again. And so now we're going to put them in here. Okay, I don't know what's happening here. Hang on. There we go. Okay. Technical difficulties. Okay, so we were right back to this where we had erased, so we'd erased two of our dots from each oxygen, and we're going to go ahead and move them in. And now we've got 2, 4, 6, 8, 10, 12, 14, 16. So we've counted our electrons. We've got octet on everything, so we know that we're good there. All right, and now let's go ahead and say, okay, what is next? And what we have here is, you'll notice that we have number 3 says our number of bonding pairs. Okay, so this is tricky. These are double bonds, but double bonds only count as a single site, just like single bonds do. So we have, you could say that we have 2 double bonds. And in that case, that's going to count for our number of bonding pairs. It's still going to be 2. All right, and then number 4, we're only looking, this is really important here, we're only looking at the center atom for everything. So on this carbon, we have 0 lone pairs. Okay, which means that we have basically we have 4 or 2 because it's 2 total sites for our pairs. Okay. All right, so now let's take a look at what the geometry of our molecule would be. And so first of all, we can see that because there's nothing else on the carbon, we've got this 180-degree angle. And the 180-degree angle means that our, in this case, what's really interesting is that 6 and 7 are going to be exactly the same because there are no lone pairs. So that means for both 6 and 7, our molecule is linear. All right, great. So now let's go ahead and look at our arsenic pentabromide. Arsenic has 5 valence electrons, and we've got 5 bromines at 7 valence electrons each, which gives us 40 valence electrons. Okay. And so let's go ahead and build this. This means that we have 5 bromines on our arsenic. So I'm just going to go ahead and start like so. And this means that I currently have 10 electrons in current bonds. And so then I've got 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. So this one was pretty easy. I just needed to count them up and now I'm good to go. Okay, so I've got 40 electrons and I can see, interestingly enough, on here that here I have these 5 domains. And so let's go ahead and count, let's go through all this. Okay, number 3 is our total number of bonding pairs, and our total number of bonding pairs on the arsenic is 5. And I'll just say BP for bonding pairs. And then number 4, we have 0 lone pairs. And for number 5, that means that we have 5 total pairs. And this is going to make sense when you get to the actual lab itself. Okay, now, again, with this one, for 6 and 7, we don't have any lone pairs on the arsenic, and because there's no lone pairs on the arsenic, geometry of our electron arrangement and the geometry or shape of the molecule are going to match. Okay, and so we've got 5 sites here, and if you look back in your notes, you'll see that 5 bonding sites is a trigonal bipyramid. Okay. All right. Let's go ahead and go on to the next set. Oh, hang on. That's not what I want to do. Give me a second. I need to um, teaching on Zoom isn't always the easiest thing in the world. Okay, so what we're going to do is we're going to pull this up like this. And I want to leave what I have on the side. So I'm actually going to full out erase what's here. Usually I would just clear all of my drawings. There we go. All right. And okay, so let's look at CH4. And so our first step here is to count our valence electrons. We've got 4 from the carbon and 4 hydrogens at 1 each. So we have 8 valence electrons on this one. This one's nice and easy, much easier than the ones we started with. I'm going to start with my carbon and I'm going to place my hydrogens around it. And when I do that, I see that I have 8 bonds, 4 bonds with 8 electrons. And so I'm actually done. It was that simple. Okay, so now we have number 3, which is our number of bonding pairs. And that's going to be 4 bonding pairs on the carbon. And number 4 is going to give us 0 lone pairs. And so number 5 is 4 total pairs. Okay. And then we're going to go ahead and take a look at our geometries. And if we look up for domains, we will see that it is tetrahedral. And you'll notice with this one as well that 6 and 7 are going to be the same because we don't have any lone pairs. Okay, so these are this we got into some simple ones here. Now we've got boron trifluoride, and so that's 3 for the boron and 3 times 7 for the fluorines, which gives us 24 valence electrons. Okay. And now we remember that boron is one of the exceptions in that it usually doesn't match the octet rule. And that's because it just has those 3 little electrons right there. Okay, so what we'll do is we've got 24, we've got 6 here, 8, 10, 12, 14, 16, 18, 20, 22, and 24. And this is going to be, this molecule is totally stable because boron is one of those exceptions. And so when we take a look at this now, what we're going to sort of start counting everything up here. And so for number 4, that should be a 3. For this one, we have 3 bonding pairs. We have 0 lone pairs. And so that means that we have 3 total pairs again. These are much easier than the ones we started with. All right. And then notice again that we have no lone pairs on the center atom. And when we have no lone pairs on the center atom, 6 and 7 over here are going to be the same. And these are going to be trigonal planar. All right, great. So now let's look at HF. So we have 1 valence electron from the hydrogen and 7 from the fluorine. So this one has 8 valence electrons again. Now this one's just a tiny little molecule, hydrofluoric acid, H to F. And so we're going to be like, okay, well, let's go ahead and put in our lone pairs. And we know that on hydrogen, we don't have any lone pairs, but fluorine, of course, is always going to have 3 lone pairs or 6 electrons. And now we have all 8 of our electrons right there, so we're good to go. Now, this one is a little bit different in that we can't really fill any of this out because we don't have a center atom. Okay, so for this one, because we don't have a center atom in this case, we're not going to count any of these. And when you find this one in there, so you can leave 3, 4, 5, 6, and 7. You can just leave these blank because we don't have a center atom. Sometimes people will say, well, this molecule is obviously linear. And you could say that because, if you look at fluorine, we have these three lone pairs here. So you can see, well, fluorine is tetrahedral. Um, and you can kind of do that if you want to, but because we don't have a center atom, it doesn't make nearly as much sense. So we're just going to not do anything for that one. Okay. Now let's take a look at H2O. So here we've got two hydrogens at one each, plus 6 for the oxygen, giving us 8 valence electrons. I clearly liked the number 8 when I was doing this. All right, and we go ahead, and you've seen me draw this before, so you know kind of why I place it like this already, and that's so that I can think about my geometry. And here I have 4 valence electrons already in there, and I will put the other 4 here so that I'm filling oxygen's octet. Okay. And then what I'm going to do is now, in this case, oxygen is our center atom. So this gets a little different. This one has 2 bonding pairs. Okay. And it has 2 lone pairs. So that means that it has 4 total pairs. And we use that 4 total pairs to determine first the geometry of our electron arrangement, and that's going to be tetrahedral. And then we basically ignore the lone pairs here when we're finding our shape, and we look back and we see that that means that this will have what's known as a bent or angular shape. Okay. Let's go ahead and go on to the next page. Oop. All right. Okay, and again, I need to erase all my drawings here. Only I could leave the ones everywhere else. Just bear with me. Skip ahead until this part is done. There we go. Okay. So here we go, back to our drawings. And now we have I3, and notice here that there is this one, it has a charge on it. Okay, so that's going to be important in a couple places. So first of all, we have 3 iodines at 7 each, and that's 21, plus one more from that negative charge, which gives us 22 valence electrons. And so I'm not quite sure what this is going to look like. So what I'm going to do is I'm going to basically just kind of start by doing this and see what happens. Okay, so right now I can see that I have 4 accounted for already, and let's go ahead and just start putting up the rest of them. So I've got 4, and then 6, and then 8, and then 10, and 12, and 14, and 16. And then I stopped to think, wait a minute, I've only got 16 on here, and I need 22, which means I need 6 more electrons. And then what you got to do is you got to remember that oxygen can expand its octet. Sorry, not oxygen. Oxygen cannot expand its octet. Iodine can expand its octet, okay? But we can only expand the octet on the center iodine. And so what we're going to do is we're going to put 6 more electrons on the iodine, and I'm going to place them kind of like this. And the reason for that is so that I can show where these lone pairs are going to be. So there's one set of lone pairs and one and another one right there. And what you kind of want to see from that is that this is going to make kind of this triangle like this. Okay, and that's going to be important when we're thinking this through. Okay, so first of all, we get to number 3, and you can see that the center iodine has 2 bonding pairs. And number 4 means that it has 3 lone pairs. And number 5 means that it has 5 total pairs. Total. Okay, so now we need to think about our next piece here. And number 6, the geometry of our electron arrangement, we've got 5 things on the center, which means that this is going to be a trigonal bipyramid. And number 7, if you look at your sheet, you'll be able to see this. But so we've got this triangle in the center, and those are the 3 that are in the center. And then the ones on either side are the ones that are left over. So that means that our molecule is going to be linear. And again, go back to your slides. You've got a diagram in the slides that kind of goes through all that. Okay, now let's look at SF4. And SF4, so we have 6 from the sulfur and 7 for each of the 4 fluorines, which gives me 34 valence electrons for my SF4. And because I kind of know how this is going to look, I'm going to go ahead and just sort of start going with that here. You don't have to do it like this, obviously, but it's going to make it a little easier to see what we're doing. Okay. All right, so here's my fluorines, and now I'm going to start putting in my dots, and I've got 2 here, and 2 here, and 2 here. So now I've got 4, I've got 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and I've got 2 left. This is why it's so important to count your valence electrons, because otherwise you're going to look at this and think, oh, I'm done. You wouldn't have drawn it like this, but now I can see, okay, I have these up here. Okay, and that is going to, there's a nice big, lone pairs really push on the geometry quite a bit. Okay, so then I come over here and I have 4 bonding pairs, and I have 1 lone pair. And so I have 5 total pairs. And so that means that 5 total pairs means, just like this one, that this is going to be a trigonal bipyramid. And then number 7. Our shape is going to be seesaw. And it'll look kind of like a teeter-totter. All right, now let's look at our PF3. Phosphorus has 5 valence electrons, 7 for each fluorine, which gives us 26 valence electrons for our PF3. And now for this one, what we're going to do is again, I'm drawing these in a specific shape because I already know what they look like. It's okay if yours doesn't look quite like this, but I know that phosphorus is always going to at least follow the octet rule. So I'm not going to place this as though it were boron, because that wouldn't make any sense. So I need to leave a spot. Like I said boron and did boron. Phosphorus. And we'll put our fluorines around our phosphorus like so. And currently I have 6 electrons accounted for, and then I have 8, 10, 12, 14, 16, 18, 20, 22, and 24. And I'm going to put the last 2 right there, so phosphorus's octet is full. And switch things around there. Okay, so now we take a look at this and we say, okay, well, our 3 here is that we have 3 bonding pairs, And number 4 tells us that we have 1 lone pair. And number 5 means that we have 4 total pairs. And 4 total pairs means that we are back to a tetrahedral electron arrangement. And because we have this lone pair up here, that means that our geometry or shape is going to be a trigonal pyramid. Just a couple more. All right, we have xenon tetrafluoride. Now, this is one of those weird cases where we're going to get our noble gases to bond. And so we have 8 from the xenon and 7 for each fluorine, which gives us a big 36 valence electrons. Okay. And we're going to place our xenon here. And then we've got our fluorines. Okay. And we'll place our dots. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've got 4 more. We can't expand fluorine's octet, but we can expand xenons. So we've got 2 and 2. Okay. And so we need to make sure that we account for these when we're working through this. I'll go ahead and put a little right there as well. Okay. So number 3 here is that we have 4 bonding pairs. And number 4 says that we have 2 lone pairs. And number 5, then, that we have 6 total pairs. And that means that we have number 6 is going to be octahedral for those 6 pairs. You might be thinking, okay, well, why octahedral for 6? And the reason for that is because 6, having the 6 points, the 6 makes basically a two-sided, two halves of a 4-sided pyramid. So there are 8 faces on this. It's kind of tricky to imagine. But because we're missing these 2, our overall geometry or shape is square planar. Okay. Now I'm going to assume that you guys have these all written down, and I'm just going to go ahead and erase everything at this point because that's going to make that a little quicker. And we'll come down and we'll do the last 2. And our beryllium, now beryllium is tiny. Beryllium only has 2 valence electrons and then 7 for each chlorine, which gives us 16 valence electrons. Beryllium is one of those weird ones where it's an alkaline earth metal, but it also forms actual like bonds. So it's a little bit different. And we know that beryllium is one of our exceptions. It's stable with only 2 bonding sites. And then we'll pop in our chlorines like so. And we've got 4, 6, 8, 10, 12, 14, 16. So we're completely accounted for at this point, which is great. And then just kind of to go through this, we have 2 bonding pairs. We have 0 lone pairs. And so we have 2 total pairs. And using what we had done before, our 6 and 7 means that both of these are linear because that's as far as they can get from each other. All right, one more, and then we'll be switching gears a little bit. Here we have sulfur, which is 6 valence electrons, and 7 for each fluorine, which gives us 48 valence electrons. So just looking at this, we automatically know that this is going to be an expanded octet. And we'll place all of our fluorines. And then we'll start counting. So I've got 10 and 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, and 46. Okay, I did something wrong. So I can't, clearly counting by twos is challenging for me today. But if you look at this, each, we've got one line and six. So each fluorine has 8 on it, and there are 6 of them, which adds for 48. I'm not going to recount them all. That sounds silly. And when we look at this, then that means that we have 6 bonding pairs, we have 0 lone pairs, and we have 6 total electron pairs. And because we have no lone pairs on the center, that means 6 and 7 are going to match, and they are octahedral. All right, so hopefully that is an amazing review here. And what I'm going to do is we're going to clear everything. And we're going to stop the share. Hello. And what I'm going to be doing here is I'm going to hold up models. I'm actually going to move so you can see these really well and kind of lean over from the side. And I'm going to hold up models that match. And what you're going to need to do is, oh, I already put this away. Hang on a second. I won't bring it back up. But you're going to be working off of this. And I'm not going to do the example at the top because I think you guys pretty much get it, but you're going to be filling this in. And you'll notice from there, you've got the total number of electron pairs, total number of bonding pairs, total number of lone pairs, geometric arrangement of the electron pairs, geometry of the molecule, and an example from pages 1 and 2. Okay, so what you're going to be doing from 1 and 2 is you're going to be basically comparing these with one of the ones that we did on the other sheet. Okay, so let's go ahead and take a look at these. First of all, we have number 1. Let's see if I can. And here is our number 1. I don't think it's working for me to stand up. I thought you'd be able to see it better, but here we go. Number 1. And here you can see our number 1. Okay. And here is number 2. Everything's mirror imaged when we're working on these. And here is our number 3. You can see what's on here. Here is a funny one. Here's our number 4. You can probably tell what those blue things are, right? Here is our number 5. You can kind of see how that works. Count them. Pause the video if you need to add things up. Got number 6. And oh, that's kind of hard to hold it. So kind of take a look at how many we have here. So with this one, I'm going to go ahead and kind of show this. Here we're on. You can see, so you've got 2 that are upright like this. And then if I rotate it, you can see that it makes that triangle in there. So that should kind of give you an idea of what that one would be. So here is number 7. And I think this works better. And here you can see you've got these 2 here. These are lone pairs. Okay, and then the those there. Oh, nope, that went in there. Okay, and here we have number 8. And a nice big one here. So you can see here that you have these top and bottom. And then if I turn this on its side, it forms, you can kind of see this here. Ooh. Okay, and it makes kind of this, like, you can see the square in the middle and those on the side. Grabbing the wrong ones. Okay, sorry. And here's number 9. And now this one, you can see you've got, it looks like a top and bottom, but if we rotate it like this, you can see these 2 lone pairs up here, top and bottom. And then here you can see kind of a square there in the center. That should help. And then here we've got a super funny looking one. This is number 10. Okay. And you can see that we've got 3 here in the plane. And then if I turn this over, it looks like a propeller. And we've got 3 lone pairs on that center atom. Got our number 11. And this one's kind of funny looking. Let me see if I can show what this does. I think this one is super fun. Hopefully it'll remind some people of their childhoods. And what does that make you think of? So hopefully that is a nice little clue. And last but not least, we have this cute little one here, which looks super funny. We've got a little one here and a big one with all these great big lone pairs on it. Awesome. That's your lab. Don't forget to turn it in.